Welcome, everyone, and good afternoon. My name is Jacob Hayden, and I am the program coordinator for SaferSim at the University of Iowa. SaferSim is a Tier 1 university transportation center with the research priority of promoting safety. And our webinar series features the research projects from within our center. So thank you for joining us today. There will be time at the end of our presentation for questions and discussions. Attendees can use their microphone or the chat box to participate, and feel free to use the chat box at any time throughout the presentation as well if you have a question or comment. Today's webinar features a research project from the University of Puerto Rico, Mayaguez, and I'm pleased to welcome our presenter, Alberto Figueroa-Medina. So welcome, Alberto. I'll turn it over to you.
Okay, good afternoon. Thank you, Jacob, and welcome everybody. Good afternoon. My name is Alberto Figueroa, and I will be presenting today on behalf of the UPRM Safer SIM team. Some of the results we obtained from this study related to gap acceptance and walking speed using virtual reality simulation. I want to thank Dr. Don Marshall, Director of the Safer SIM Consortium and the UTC program for inviting us to present this afternoon. So moving on, let me see. Okay, let me first present the research team that worked in this project. Dr. Didier Valdez, who is also the director of the Safer SIM program here in Mayaguez, and Dr. Colucci were both co-PIs in the project and are also professors in the civil engineering department, along with myself. And we had three graduate research assistants, Natasha Cardona, who is from, she's a master student of civil engineering, and Andres Chamorro and Dr. Alcibiades Bustillo, who are from the computer science and engineering. So basically today I'm going to talk about some of the details about the project that we concluded the first phase, including the research statement, the objectives for the study, a little bit about the methodology that we follow for the study, and the main results from the analysis with the main conclusions from the study. So to start, I'm going to talk about a little bit about the review of literature that we perform, and to provide a background justification for the study. You know, pedestrian fatalities in the United States have increased significantly between the years 2009 and 2018. And it got to the fact that pedestrian fatalities in 2018 was the largest number recorded in the US, in the United States, since 1990. Crash data shown that 75% of fatalities happen in urban areas outside of intersections, such as mid-block crossings and under dark conditions. In the case of Puerto Rico, our pedestrian fatality rate for the year 2019 was 3.1 deaths per 100,000 people, while the US average rate was 1.9. So Puerto Rico, the rate for Puerto Rico was the fourth highest from all US jurisdictions. Also, data from Puerto Rico shows that 1/3 of the fatalities were related to pedestrians, with 90% of those events happening outside of intersection, and 88% of the pedestrian fatalities related to an improper action or traffic law violation made by the pedestrian. So for us, it's a very critical issue attending to pedestrian safety in the island. So in terms of behavior, it is widely accepted that pedestrians will tend to search for the shortest route. So that means that people will cross outside of intersection, even at high volume and multi-lane urban streets. So mid-block across the literature is recognized as location with a higher potential risk for crashes, considering that pedestrians need time to safely cross the street, weighted against their perception of the approaching vehicle speeds. So that becomes a very critical issue in terms of safety, and either by drivers' failure to yield the right of way to pedestrians, or the improper crossing of roadways or intersection by the pedestrians are two key elements in highway fatalities related to pedestrians. And when we analyze the decision of the pedestrian related to the gap acceptance, we had to realize that the decision to cross the street at an uncontrolled location focus on the capacity of the pedestrian to accept or reject the gaps between two consecutive vehicles. At higher vehicle speed, pedestrians try or tend to make riskier crossing decisions and accept smaller gaps. There has been several studies done related to gap acceptance. One of those, Kadali and Bedagiri in 2013 concluded that the pedestrian gap acceptance depends on walking speed, the vehicle speed, the direction the pedestrian is going, the rolling gaps, and the age of the pedestrians. Other researchers have found waiting time and the number of lanes as significant factors that affect gap acceptance of pedestrians. And as you know, street crossing events, as happens with many other highway safety issues, tend to be highly impacted by human factors. And the literature shows that in specific for road crossings, street crossings, older pedestrians and males are overrepresented in crashes when you compare them with their counterparts. Older pedestrians tend to make more unsafe decisions and are less able to safely cross a street due to the presence of health, mental, or physical conditions, and also have reduced risk perception. On the other side, the male pedestrians tend to make riskier decisions and are less willing to wait for gaps in traffic and are more disposed to violate traffic rules than their female counterparts. So these factors obviously take a lot of significance in this type of study. When you do observational studies of pedestrian behavior, on the past, we have relied on manual data collection, video recording efforts, and the benefit of these studies are obvious. You are directly collecting the user behavior as it occurs in real life. But they have some disadvantages or drawbacks from this type of studies. For example, the setting of equipment at different locations, that you are make certain that you have all possible locations, different settings, that you have the necessary combination of factors for the study, but you have also to consider the cost, the safety risks for the collectors, the equipment, and the pedestrians. So obviously it's not an easy task. But recent developments in virtual reality has bring a lot of promise to the study of pedestrian behavior using safe and controlled environments. This study that we are going to present today is the initial effort that the UPRM Safer Sim team had with the use of the virtual reality equipment as a pedestrian simulator. So the objective of the study was to simulate street crossing and measure the capacity of pedestrians to select safe gaps between vehicles and walking speeds when crossing an urban street. In terms of the benefits, the literature shows that the benefits of virtual reality is the interactive simulation, the implicit interaction, and the sensory immersion that allows us to recreate real-world experience. Other researchers have used virtual reality technology already, such as our Safer Sim College at the University of Iowa, Dr. Kearney and Dr. Plummer. They have done previous studies in the past using virtual reality, and they have shown the promise of this technology in being able to study the human brain and its reaction. Other researchers have also concluded that virtual reality is more than capable to replicate real-world behavior from pedestrians. So basically, we are having this time as a methodology using 7 steps. 2 of the first steps were the training of the research team on the use of the virtual reality equipment, because as I said, this is the first time we use it, and the creation and the coding of the virtual reality scenarios. So when we started this, we had the help from the team from the University of Iowa. So I want to recognize Dr. Joseph Kearney and his research team that gave us access to their lab. One of our research assistants went to Iowa and they gave him a crash course on the coding they were using on the research study. And once we understood the logic that the Iowa team was using in their simulation study, we were able to complete our scenarios, perform a pilot test to fine-tune the experimental design and to conduct our simulation runs. So in our case, we had two virtual reality headsets, but the one we used for the data collection was the HTC Vive Pro. We acquired this headset very early in 2020, although we did the initial setup of the study using the HTC Vive, which is an earlier model. That one, although it has a lot of potential for use, it has a smaller detection area and it was connected by a wire. This new device, the HTC Vive iPro, has a wireless antenna and has a larger detection area up to 32 feet by 32 feet. So this device allows us to increase the opportunities for having different street crossing situations that the other device, the HTC Vive, didn't have. And also this one, although we didn't use it in this project, it has two handles and also you have eye tracking capabilities for further studies on how people behave and react. So in our context for this study, we had two contexts in terms of scenarios or configurations. The base scenario consisted of a 900 feet long straight segment of urban road, either with one lane or two lanes. It also included two sidewalks, obviously one of each side. And the road geometry, the city context, we built it using AutoCAD and SketchUp, and then the rendering of the design was improved using the Unity software. The road network that we created included two intersections with a main segment, that is where the traffic was going in the experiment, to provide the subject with a more realistic perspective, allusive to a city with small blocks, approximately 200 feet long blocks, a little bit more in some cases, of a representative city. And the crossing was located at more or less the middle of the segment. We programmed the traffic to not react to the presence of the crossing pedestrian. So basically the traffic will not yield to the presence of the pedestrian. They will continue moving at the same speed without reacting to him or her. In terms of the experimental designs, we had three configurations. Two configurations related to the one lane setting and one configuration related to the two lane scenario. We used traffic parameters of traffic speed and vehicle gaps. We changed those two parameters. Traffic speed was fixed at either 15 miles per hour or 25 miles per hour. The 15 mile per hour speed was associated with an average risk of severe injury of 10% for those pedestrians getting struck by a vehicle. And the 25% speed is representative of an average risk of fatality of around 10% as well. So obviously these are low speed, 15 and 25 speed in terms of the overall general character of the roadway, but still there are some risk involved to the speeds. Also vehicle gaps, we set them up at either 3 seconds or 5 seconds for the one lane street. We also had a third setting using random values from 2 to 5 seconds in half a second increment for the one lane road. For the two lane street, we didn't have the fixed gaps and we went with a random gaps from 2 to 8 seconds, but we did include the two speeds, 15 and 25 speed. Age and gender were blocked in the experiment. We had 4 age groups and the sample was equally divided into men and into women. Overall, we had 48 subjects that participated in the study, each of them making around 10 to 12 simulation runs, each one of those voluntary subjects. Now I'm going to show you a quick video. You can see we have an overlap of the experiment on the top left corner. We have Natasha wearing the headset, and we have Andres working the computer to activate the scenarios. And you will see very quickly, this is a 2-minute video of the two-lane crossing, urban crossing setting The video doesn't have any sound. In the reality, the simulation did have the traffic sound and the urban city environment. We have some radios and so on, so people will immerse in the actual, virtual setting. And we also included, it just passed by a billboard. And now when you see, look at the building, and you can see a billboard. That billboard had two lines of information. The first line was the trial number. So the subject knew how many rounds he already had. The second one was a little bit more interesting. It had, in such cases where the pedestrian didn't cross the road safely and he was struck by the vehicle, a message saying in Spanish, fue atropellado, you were hit in English, appears in the billboard in red capital letters, so people will know when they are getting hit. And the purpose of that was to allow the subject to be alert, to know when they cross safely or not the road. So in some way, they were alert that their speed was not adequate to safely cross the road, and they were hit by the car, and also to incentivize them to make their best effort, to recognize that they are being evaluated by their performance, so they will be incentivized to make the best effort to get to the other sidewalk without being hit. As you can see, she already did the first run. And then when they go back to the original sidewalk, the traffic stopped. And now traffic is coming again. They had to wait until the first vehicle to go out to pass the crossing, and then they will start analyzing the gaps in traffic and the vehicle speed to understand when they should cross the road. And once they did that, you can see we did this in purpose. It comes the red letter saying, okay, you were hit. That means that you didn't do a good job crossing the road, and that provides immediate feedback to the pedestrian. And we collected that data as well. Okay. So in terms of the results, I'm going now to discuss some of the results in terms of the number of gaps seen by the subjects, the accepted gap that they took to cross the road, the average walking speed, and the street crossing success rate. That's how we call that variable of successfully crossing the road. And I'm going to talk about a little bit about the details of these results. Obviously, on the report, you can see more details. Let me show you the number of gaps seen, grouped by a scenario and by traffic speed. And this is the one-lane configuration. As expected, the highest number of gaps seen by the subject were for a scenario 2. Scenario 2 is the one in the middle of the three columns. Scenario 2 had the vehicles generated with the short constant gap of 3 seconds. And that was the hardest crossing situation. As you can see, 7 data points had over 40 gaps. So these people waited 40 gaps before deciding, at least 40 gaps before deciding to cross the roadway. Surprisingly, traffic speed didn't appear to have a strong impact on the number of gaps. As you can see, on the top is 15, and on the bottom 25 miles per hour, and they don't appear to be too different. On the other hand, a scenario 3 on the right side of the columns of the graphs was the easiest crossing situation with the constant 5-second gaps. As you can see, the number of gaps, it was very low in that scenario, and that's also is expected. When you see scenario 1 that had the random variable gap between 2 and 5 seconds, it added an uncertainty effect to the situation of crossing the roads. All runs, except for 2 points, exhibit gaps seen values of less than 15 for the random. Although this scenario was construed as an intermediate crossing difficulty, the reality is that the results from a scenario 1 was very similar to the easy crossing of a scenario 3. We also had the opportunity of checking age and gender differences in our sample, not representative for the population. But when you see those difference between the groups are more clear now. You can see now the scenario 2 has the highest number of gaps gap scenes, but the effect is much more intense for the group of 66 to 85 years old. Interestingly, the effects of the vehicle speed and the gaps are not similar for female and male groups in our sample. In configuration 1, females tend to wait for more gaps as the age increases, whereas the males tend to reduce their number of gap scenes, except for the senior group. The senior group has a higher number of gap scenes, as you can see by the brown columns. For scenario 3, that group in configuration 2 was the only that exhibit an average value gap over 10. So they waited more than 10 gaps in order to cross. In the case with random gaps, the male group of 66 to 85 again show the highest number of gap scenes. So this could represent that the sample that we obtained of those objects was composed of risk-averse individuals. They didn't want to take a lot of risk when crossing the road. When we go to the average walking speed, we see the histogram or the bar charts for the number of or the walking speeds. Let me go a new one. Okay, this one. Sorry. So the frequency histogram of the average speed show a considerable accumulation of subjects walking between 3 and 5 feet per second. A small group of subjects has speed greater than 6 feet per second, and that makes the distribution skew to the right. It didn't follow normal distribution. In our pilot study, the data, the sample behave like a Weibull distribution. So when you go and check the variance, now you see different settings. You see the 85 percentile speed was 5.3 feet per second. Those individuals had 3.75 seconds to cross the road. So when they do the crossing, they had enough time to cross without having a problem with the vehicles. When now you go, sorry about it. Now let's go forward. When you go to the 15 percentile, it's 3.1. So those take 6.4 seconds to cross the road. So now you have a problem. You have these people who walk slower and might come into a problem having to cross safely from one side to the other with a difference of almost 2.5 seconds, a little bit over 2.5 seconds more time on the roadway, crossing the road. So when we check the gaps accepted by the individuals, you can see at different speed, they don't really are too different. But when you see the difference between the 1 lane and the 2 lane, now you see on the 2 lane crossing, the accepted values for the gaps are much higher, 2 seconds, almost 2 seconds higher for the 2 lane compared to the 1 lane. And that also has a problem when you check now walking speeds, accepted gap, and traffic speed. Now you go back to the 85 and 15 percentile, and you see now those two who take 3.75 seconds are fine. But now the gaps, look, the 15 percentile accepted gap goes from 5.8 to 6.2, and the 85th percentile 7.2, 7.4. So now these people who take 6.4 are not consistent with the different gaps that they accept to cross the road. And that's when you get into trouble getting hit. And we recorded that, and that's my last result that I'm going to discuss today. When you check the street crossing success, that was calculated for all the subjects, and you can see that none of the subjects on the easiest crossing situation in the 1 lane configuration was struck. It was too easy, so they didn't have any issue crossing the road. But on the other hand, for the hardest crossing scenario, number 2, the lowest success rate was 80% for the high speed, for the 25 miles per hour. So that starts telling you that there is a problem with walking speed and the gaps. There's no correspondence for everybody. And when you go check gender and age, now you can start looking at difference, and you can see that the male group had somewhat in one of the groups have a better success rate but not in the other. In the 2-lane road setting, the trend is reversed. Females had a better crossing rate. When comparing age group, you can see again that the worst crossing success rate was for the 68 and 85 cohort with 90%. So again, senior pedestrians had issues with successfully or safely crossing the road, selecting their speed, accepting a good gap in traffic. So in conclusion, now with the virtual reality technology, we can develop new experiments that will allow us to collect behavioral data for pedestrians and other road users in control and safe environments, while accounting for many factors that affect road user performance that we can do it in real life, but it might be too complex or too costly to include many factors that we can do in a virtual reality scenario. So in conclusion, because I know I'm running out of time, the second phase right now, we are working on a road information assistive system with their virtual reality. What you are seeing on the screen is like a tablet that the person will have in a connected environment. And that tablet will give information about traffic in terms of speed, gaps. So people will have information about how to cross the road, and we will check if this will be positive or negative in the sense that it become a distraction, a new distraction for pedestrians. So we will see if it works good or it works bad. Very, if it's a good idea or is this a bad idea. So thanks for your attention. I think we still have some time for questions. So Jacob.
Definitely. Thank you, Alberto. And that's music to my ears hearing the collaboration success between UPRM and the Hank Lab at Iowa. So that collaboration is vital to our center and SaferSim and across the UTC program in general. And I will shout out a couple other Hank Lab researchers that are actually on the call today, Doctors Elizabeth O'Neill and Kyle Rector. So, but with that, we do have time for questions and comments. So if anyone has any thoughts or questions, feel free to use the chat box or unmute yourself. And
hi, Jacob. This is Joe. I just wanted to say to Alberto, a great job. I'm really pleased to see that you've come so far and your environments look spectacular. So great job. I was interested in seeing your result, and it was fun to hear your talk.
Yeah, like I said, we owe you a big thanks. When we go back to Iowa, big hug and big thanks because you help us understanding, obviously learning from your experience, what you have done with virtual reality and your other studies. So thank you very much.
Excellent. Well, you're always welcome to come back to Iowa whenever it's safe to do so, obviously. The doors will be open. I will share a couple other things before we wrap up. So again, if any other people have questions, feel free to unmute yourself or type in the chat box. I do want to share that this presentation will be available on our YouTube channel and our website in the next couple of days. We will send that link to you and all the registrants once it's available. So feel free to share it with any colleagues that may be interested.
I guess I have a question, and acknowledging that it didn't have an effect on your results, that you clearly had interesting findings. But for the VR avatar, I noticed it was a young woman and you're looking at different ages and genders. So I was just curious if that avatar is the same for all participants or if there's like different avatars for different participants.
No, they're the same. We had people walking, avatars walking on the other sidewalk. We had, you see a young lady standing right next to the crosswalk. It was sort of in the way, so people, have to move their head a little bit to see the traffic. And we also had a dancing boy trying to, distract people from seeing the traffic. But everybody had the same avatars in the simulation.
Thank you.
I thought I saw the dancing person doing a backflip on the sidewalk, but I wasn't sure. So was the actual participant's avatar that wasn't the like the lady to the next to the, I guess, left of the view? That was a different pedestrian that was supposed to be obstructing.
Yeah,
obstructing the view.
It is one. This avatar was standing there, just like she was waiting for somebody to pick her up or something like that, or cross the street. And she was in a view that somewhat block the view from the person with the virtual reality. So people had to, you know, move forward, backward to see traffic, and that was actually, you know, the intention, you know, to make it a little bit harder, not to see traffic at that point.
Thanks for clarifying. I thought the avatar was the participant, so that clears up a lot. Awesome.
Yeah.
Alberto, this is Joe again. How did you do the avatars, the characters that were in there?
Well, to tell you the truth, that was Alcibiades and Andres. I don't know if Andres is connected, that he might answer where he got the avatars. I don't see. Obviously, those are library avatars that Andres and Alcibiades added to the simulation. So obviously, you can get in touch with us, and we will provide the details of what we did and share with you any of those simulation files.
Great, thanks a lot, Alberto.
Mm-hmm.
Okay,
Hi, Alberto.
No, please go ahead.
Okay. This is Elizabeth O'Neill from the Hank Lab. I guess we're a chatty bunch today, but I was curious what motivated the gap size choices that you guys had for your scenario, because we often find that people don't love a 3-second gap, and it's challenging, which can be good, but that's just in a single lane of traffic. And to go along with that, was the configuration of traffic always what you saw here with the leading car being in the far lane?
No, well, that was randomly assigned for the 2-lane scenario. So it can be the near or the far. That was random set up in the scenario. Why we choose the 2 and 5? To tell you the truth, we started with the same range that Iowa used in their experiment for the 1 lane. But for the 2-lane, we try to expand that a little bit. Remember, this is the first one with the first study we did. So we saw that from 2 to 5 for the 2-lane, it was too complex. It was going to be too complex for the people to cross. So we expanded that a little bit. We went up to 8 seconds. And that obviously had an effect on the gaps they took. But other than that, obviously, let's say this is an engineering judgment call that we based on literature, what Iowa had on their studies, and using our judgment.
Sure, thank you so much.
Mm-hmm.
Excellent. And I didn't mean to cut you off, Elizabeth, but I know we are a little bit over time, so I know we're all busy people. So if we do have to run, I think that might be a good spot to end it. If you have any follow-up questions or comments, reach out to me or the UPRM team, and I'm sure we can help you with anything you need. I will say our next webinar is Tuesday, March 23rd, and it's another project from the University of Puerto Rico, Mayaguez. Carla Lopez del Puerto will discuss driver safety assessment in 2-lane rural work zones. So we'll be sending registration info in the next week. And with that, Alberto, thanks again for the presentation. And everyone, thanks for joining. We will see you at our next webinar. Thanks.
Okay, thank you very much.